Chapter 15. This is going to be dealing with our wired LAN technologies. That's going to include our 802.3 standard, which is known as Ethernet. Big part of this chapter is the wired guided physical transmissions. Week 3, we actually cover, I think, 6 chapters altogether, and all of this is dealing with pretty detailed material. So I'm going to be doing videos for each chapter just so that we know. So we're going to be doing things like how Ethernet is created, how is it made up, the types of fields in its header, the different versions, the evolution, some of the earlier types of Ethernet, where we're at now, our physical and logical topologies, wiring office buildings, variations, pairing of cabling, and that's it. So just 13 sections. A big part of this chapter is, again, we're discussing, or we're focusing on our LANs. So that's our local area network, and again, focusing on the wired functionality for this chapter. So, one of the big things here is, as we progress within our Ethernet standard, is keeping everything backwards compatible. And that's actually really interesting because not a lot of technologies stay backwards compatible, meaning as we grow and develop new technology, eventually we have to drop older technologies. Ethernet really wasn't like that. And the nice thing with Ethernet is it's really evolved very heavily in the last several years. And that's not just with the devices or the cabling. The actual Ethernet itself has changed, because it used to be a very fixed set format, and now there's a lot more flexibility with that. So what does the frame format mean? So basically, the frame is at layer 2, we're dealing with the frames. At layer 3, we're dealing with packets. But it's how is that data organized before it's sent on the wire. That's what our header portion is. A big part of that is also dealing with how we do the formatting. If you think of mailing a letter via an actual postal service, like your mailman, how do we lay out that letter? We have our source destination, top left hand corner, stamp top right hand corner. We have the actual destination, the sender, but how do we do that? The sender, how do we do the destination? Name, address, city, state, zip, country code. That's all a very specific structure or format. Our frame is the same way. It has a very specific structure. And that structure in a basic format is a header, which is 6 bytes for the destination, 6 bytes for our source. So what does that actually equal? That should be 48 bits. And then we have 2 bytes for our header. That header detail should also be 2 bytes. Should actually be 16 bits. So all of this together should allow for the first set of bits and the rest of it as a payload. So the payload actually is just an envelope from layer 3. So this is actually going to have its own header for layer 3, its own payload for layer 3, and then it's just an envelope inside of an envelope inside of an envelope. Because with the OSI model, we're dealing with 7 layers, and each layer packages the layer above it in an envelope. So how do we deal with our multiplexing for our Ethernet type? We've already kind of discussed multiplexing a little bit, and that is, again, being able to package a signal in such a way where we're able to share a shared media or share a common line. That way both people trying to send data are able to send it over that shared media. Here with our Ethernet, at least dealing with our layer 2 addresses, we're dealing with our MAC addresses, our media access control addresses. I know here it says we send IP datagrams and ARP messages over Ethernet, but an IP datagram is a layer 3 packet, because IPs are done at layer 3. At the layer 2, we're dealing with MAC addresses. ARP, address resolution protocol, that is actually just a lookup for our MAC addresses. Our MAC addresses are done in hexadecimal. So how do we actually do our demultiplexing? Here we have actually the ARP module and the IP module. Basically, this allows us to start separating our frames so that they can go to the above layers. So what is this 802.3 standard? 802.3 is the IEEE version of Ethernet. While it was originally developed in '83, it is not the only 802 standard. If we are dealing with wireless, like other chapters, that's 802.11. That's our wireless standards. But going back to 802.3, we actually created our layered approach, and mainly focusing with our layer 2, we actually broke that data link layer up into 2 sublayers. Our logical link controller, LLC, and we also broke it down into our media access control. So how we do that is we add additional space for our header. 48 bits or 6 bytes, 48 bits, 16 bits, 24, 24, 16, and that makes up our 64. While that doesn't completely make up our 64, that makes up a portion of it. Because here are 6 bytes, 6 bytes, 2 bytes, so that should be 14. Here's an additional 3, 3, and 2. So that's 22 bytes. That means we still have an additional 24 bytes to for our header information to go. Because here our bytes of payload is 46 forward. So again, the overall frame, the sizing of it, normally is a MTU, because that's how we measure them, of 1500 bytes. Normally the first 8 bytes of the payload will contain the snap header. That's just, again, a specialized header. But if you ever asked what's the normal size of a frame, 1500 bytes. Actually, you end up, when you start taking certification exams, you actually start getting asked questions about Ethernet frame makeup in more than just networking. I actually did a VMware course, and I was asked numerous questions on the size of Ethernet frames. So how does our LAN connect to our network? We focus mainly on that structure and that format for our data link layer, but what operates at that layer? And normally that's our NIC. Our NIC handles our address resolution, our errors, our frame recognition, sending and receiving of those frames and other data. But what is that NIC made out of? That NIC normally is a circuit board and a plug on one side. But that is our network interface connection card, or a network interface card. But its main role is a connection between our PC's bus and processor and resources to other nodes, other computers, other items, for sharing, analyzing, collecting, all of the above. while Ethernet has gone through major changes and gone through several formatting, they're still growing strong. So now we're going to get into the different types of earlier Ethernet. And that's going to be our thick and thin wired Ethernet. Normally thin net and thick net. And normally this is going to be 10 base 5. When we actually start getting into our twisted pair, that's going to be a base 10. But essentially what we had to do is we had to have a way to receive and actually transceive information from the computer to a connected cable so that other PCs could actually get it. A physical cable known as a AUI, which actually allows for the transceiver to a NIC. Basically, it was a converter. It allows you to actually take from a NIC card and be able to communicate on that thick net wiring. If you think thick net, you think really thick coax. And so how that worked is we had a thick cable, and we would tap into that cable using our transceiver, and that tap would allow our computer to communicate on that single cable. That cable would have terminators on both sides, and they would go back and forth. So that's thick net in a nutshell. Then we had our thin net. So instead of having to all share common media, here we go from one PC to another, to another, to another. One of the problems with this, though, is they're shared. So that meant if one of the PCs went down, you could actually lose a connection further down. And again, this was ran on smaller coax. ThinNet, its primary advantage was really easy, really cheap. ThinNet didn't have to have external transceivers like ThickNet. You could do it on a convenient path, but again, if one PC came unplugged, it cascaded down. So what do we go from there? From ThickNet to ThinNet, then where? The third major evolution of Ethernet was actually replacing the coax with twisted pair Ethernet. And that's what we have now. We have our Category 5, Category 5E, Category 6 twisted pair. And that is, we have 4 pairs that are twisted that allow us to communicate over it. And what that did was it allowed us to connect centrally to a device, a hub or a switch. And that would allow us to connect and communicate locally. If we wanted to communicate to another network, for example, we'd have to connect our hub or switch to a router. Because the hub and switch, they're layer 2 devices. They run off of MAC addresses. They work off of layer 2 addressing. A layer 3 device is the only type of device that can go from one network to a different network. That's important to realize. I know that's not really important for this class, but for future classes, that's super important. So what is a hub or switch? A hub emulates a physical cable, and it allows you to send or receive data simultaneously. So how do we allow communication on those hubs and switches? So what it does is, it does this thing called CSMACD, Carrier Sensing, Media Access, Collision Detection. So what that did was, if all the PCs are talking at once, they're going to start canceling each other out. So the CSMACD actually was a mechanism that was created so that PCs could not talk all at once. What this allowed the PCs to do was stop, listen, communicate. If they started sensing that they're communicating over someone else, they would stop for a random time and again send later. So that way, if 2 people are talking at once, this would go, okay, both wait a random amount of time and then try again. And then that's how our CSMA CD worked. It was an ingenious way. That way you never had multiple devices talking on the same line at once. So you wouldn't have to worry about collisions. Again, a collision is where just two things talking at once cancel each other out. Twisted pair doesn't have to follow a strict type of topology, but if you had to kind of explain what twisted pair topology would be, it'd be a star. That is, everything connects to a centralized device, and they communicate through that centralized device. So how do we understand the topology, though? What's the logic topology and what's the physical topology? On exams, they'll ask things like this, so this is an important note. Logically, that's going to be twisted pair is a connection between one device and another, so more of a bus topology. Because again, they share one part on each side, so the PC to the switch, the next PC to the switch, the next PC to the switch, those are all buses between the PC and the switch. Even though physically, while those are all buses, collectively they all make a giant star. But where does this come into play, though? I mean, where is this useful? And that's where we start wiring a building. That's where this comes into play. So if we're going to be wiring a building, we have to make a few assumptions. What type are we doing? How many numbers are wiring? What's the distance? What's the cost? Is there centralization? Is there no centralization? Is it going to be future-proof, meaning we're going to have to plan for several years? So there are a lot of different ways to do this. So here's an example of our thicknet and thinnet. But again, both of these are old, out-of-date technologies. They're not really used. So realistically, what we'd end up doing would be some type of centralized device, a hub or a switch, and all PCs connect to that. Granted, that does give you a single point of failure, that one switch, but that's why you make sure that one switch is a higher quality switch. Again, we've already talked about the importance of the evolution of Ethernet, how the development of it actually made more sense. It stayed backwards compatible. It stayed relevant. It stayed moving in a forward path. Important things to remember is with our thicknet, that's 10 base 2. With everything above our thin and thicknet, that's 10 base T. That could be 100 base T, or that could be 1000 base T. The base T really just stands for our twisted pair. And they could be auto-sensing, meaning they can determine the speed of the cable. So how we look at that is our designations, 10 base T, 100 base T, 1000 base T, or twisted pair, fast Ethernet, or gigabit, or 10 megabits per second, 100 megabits per second, or 1000 gigabits per or 1000 megabits per second, which is also equal to 1 gigabit per second. All of that matters. And then what happens if we're using specific types of cable? Will that matter? If we're using 10 base T, we just need regular category 5. If we're using 100 base T, Cat 5e. If we're using 1000 base T or gigabit, you need either 5e or 6. I know this talk about it, but what happens if we're doing 10,000 base T? Or that would be 10 gig. That'd be using category 6 or category 6e Ethernet. So again, these standards are always changing, they're always growing, always adapting. That's important to keep in mind. So what are our connectors? That's the last important one. With our Ethernet, they're a little bit thicker than a phone cable. A phone cable is an RJ11. It has 2 or 3 pairs of wires. Normally 1 pair or 2 pair, sometimes 3 pair, but the most common is 1 pair. An RJ45 are required to have 4 pair. There are 2 major types, straight through and crossover. And so the main differences between straight through and crossover is the types of devices that you connect when hooking them up. For example, if you want to hook up 2 switches and you want them to communicate, you cannot use a straight through, because what ends up happening is the 4 pairs of wires in a straight through, they don't allow for communication on certain pairs. Hence why you have to use a crossover for like devices, because the devices that are alike are expecting to communicate and listen on different pairs. So again, like devices are cross cables. Anything else will be a straight through. So what are some crossover cables? PC to PC, switch to switch, router to router. Those are all crossover cables. A PC to router directly sometimes has to be a crossover. A PC to a switch to a router. All of those are straight through. So normally this is where someone brings up, what about this auto MDXI? That auto senses and auto does this for us. So you're noticing, maybe you not specifically, but if you've been doing this long enough, you'll start noticing that crossovers aren't really sold all that often. That's because most modern devices have an auto sensing. Though it's not an official standard, it's just one of those, it's out there. So you may or may not have it. So that's going to be our auto MDXI, and that will allow you to use a straight through or a crossover, and it does the connections automatically. Last thing is, how do we wire up our RJ45 head? There are 2 standards, 56A, 568B. Again, the first one is 568 alpha versus 568 Bravo. There are 2 different standards. And what we do for a straight through, both standards, so it's an A on both sides or a B on both sides. A crossover is an A on one side and a B on the other. All that really means though is, how are the wires used? Because you'll notice X for transmission, R for receiving. Really, you just need 1, 2, 3, and 6 to do a basic transmission and receive. Though if you want higher speeds, you need to have all of them. And that's it for that chapter. Hope you have a great day. Bye.